Your TA. I hope all of you know me. And well, if you don't, you see me here. So today what we'll be doing is I'll give you guys a very brief introduction into how the fundamentals of neural networks work and how you do some of the computations behind it. But before we get to that, I have some news. So all of you have submitted task one. I've started grading it. It's all good. I have no problems with it. Task two is out. Janet is handling it. And if you have any questions about task two, that's currently out right now, contact Janet or contact any of us and we'll help you out. Your task three is going to be another group project, and it's going to be the big group project for this semester. You'll be essentially be analyzing hurricanes, how they form, what causes them to form, and where they hit over the Gulf of Mexico region, and specifically how often they're hitting the Houston region. And your midterms one and two will be online exams. They'll be open note, open book exams, but they'll be in class. So you have to bring your laptops, you have to keep your laptops charged and everything. So uh, I think it'll be in this classroom itself, not 100% sure, but it'll be all your exams are always open book and open notes, but midterm one and two will be online only and it'll be on Canvas. And midterm one is Tuesday, October 11th. I'll bring treats for everyone. So before we begin the lecture, everyone log into Canvas, look at the exam one, midterm one. I don't know what Janet called it, like test exam or whatever. Make sure you're able to run it because it requires the lockdown browser and it sometimes doesn't work well with different laptop configurations. So if anyone has trouble logging in, starting the exam, please let us know much before before the week of October the 10th. So if you can. Does anyone have any problems with starting the lockdown browser and accessing the exams on Canvas right now? All right, cool. So I'm assuming everyone here has been able to work on it correctly. And well, the meeting is being recorded on Teams. So if you have any questions on Teams, DM me because I won't be able to look at Teams while I'm giving this lecture. Okay, so everyone's what's up? Whatever. We'll ignore the name of the day. It's on October 11th, so whatever day that is, we'll adjust it. Whatever the second Tuesday of October is, Dr. Eick will handle it. It's probably a leftover from last year's exam. It's fine. We'll handle it. We'll let you know much beforehand what the exact date is. Thanks for letting us know, though. Okay, so everyone's ready. We're going to start with some visual demonstration of of how an artificial neural network explores data, right? So today, almost all of us have like worked with or seen deep learning methods like ChatGPT, LLMs, all the generative art stuff and generative AI stuff. All of them are fundamentally based on the old 1960s and 1940s Macaulay-Pitts neuron model. Now we've built on top of it a lot, but the abstraction that you see on ChatGPT or any of the generative stuff, those are mostly geared towards end users, right? But here we are developers, so we need to understand how those things are built, like from the fundamentals, from the ground up. So if you want to create your own version of like ChatGPT or LLM or any other LLMs or whatever, you need to understand how they work at the most fundamental level because well, that's what we are here to do. We are here to develop those stuff. So, but first, let me give you a couple of examples of what it looks like when a neural network is exploring the data. How and then, God, do I? Okay. So, look at this extremely creepy image. What do you think is happening here? It's an the original data set that the neural network is working on here is a data set of 50,000 portraits taken in Stuttgart, Germany. So guess what's happening in this creepy image? Anyone? Uh, Not quite. It's not identification is much further down the line than what's going on here. So what's happening right at the start? Like guess. What's up? I'm sorry? Yes, kind of. Yeah, it is essentially okay. So what's happening is this you take those 50,000 portraits and you feed it to a right now it's an outdated model called progressive GAN, and what it's doing is it is learning the how the images are similar and how they are different and how you can move from one image to another. So what it's doing, the neural network, what the neural network behind it is doing, is that it is exploring the space of like the latent space of human faces, right? So it doesn't know what humans are, which is why some of it looks so weird, gross, and like something from Saw or whatever. So it doesn't, it has no idea what human faces are, right? So what it's doing is it has blended all possible combinations and permutations of human faces, and it is exploring that space. So it's going like, say, for example, a Roomba uh, in a big mansion. So it is exploring every single floor, like all the floor, all the where the chairs are, and all where the dining tables are, where the rooms are, etc. So it is going through that entire space and it is exploring it. And what you see here is just one such random path taken by the algorithm through that entire space. Right. So that's why it's so weird because it doesn't know what is an endpoint that we are looking for. All it knows is that all these images are there, and somehow it is trying to find a path between where all these images are connected. And that's what's all these connections are what you see in between those human faces. Right. And now this is pretty old now. Like this is almost 6, 7 years old, progressive GAN, and it has been replaced by much more powerful techniques. And okay, let me show you one such powerful technique. So this is, hang on, let me again play the video so that you can see what's going on. So uh, this is a much more modern neural network. So what it's doing is, wait, it's that thing is blocking a little bit. So I can't even see my mouse. So this is what is called deep dreaming or hallucination. So what it's doing is it in this model, it knows like all the priors have been trained into this model. So it knows what roads are, what is in motion, what colors mean, things like that. Like the very fundamentals of expression are known to this model. And what it's doing is it is going through this model and it is hallucinating. Like it has been given lots of images, lots of data of taking a walk through Shibuya in Tokyo, right? And it has been also been trained on the styles of the artist Leonid Afremov. So it is combining both of these two things together, and it is trying to find something that matches what it has been trained on. So it is taking the styles of Leonid Afremov, and it has taken a video of Shibuya in Tokyo, and it has merged them together the best it can, right? And it is like these are kind of flashy, and these are good for visuals, but this is useful in lots and lots of different fields, because what it ends up doing is you give it two very distinct and very different data sets, and it finds some way to combine them together and while preserving the most important elements of both of those data sets. Now you can imagine this is useful in lots of different ways. It is useful in, for example, in geography and remote sensing. It is useful in astronomy. It is useful in drug discovery. It is useful in, for example, uh, hunting for oil. It is useful in neurosciences and lots and lots of different things where you have multiple different sets of data and you need to combine them together and you need to find out like what are the deeper insights into that data that we haven't yet been able to see. So, and if you want to, well, this particular thing was created using Google's Deep Dream project, and the Deep Dream project essentially it's kind of hard to run it on your laptops, but if you have access to, say, for example, a low-tier version of Google Colab, or if you have access to the University of Houston HPC, the High Performance Computing Center, the HP High Performance Computing Center, you'll be able to run it on your own. You train a model on some artist that you like, who is in the public domain, and then you take one of your own videos, and then you can merge them together and create something very similar to this. Even this is 4 or 5 years old right now. So modern deep learning methods are going to give you even better results. So uh, let's go right back to the start of where neural networks came from. So most of this, the very fundamental text of artificial neural networks and what like even modern deep learning methods are based on are called the Macaulay-Pitts neuron model. So this was created by Warren Macaulay and Walter Pitts from the University of Illinois at Chicago. And so they published a book called Logical Calculus of Ideas Imminent in Nervous Activity. So it was pretty much the very first purely mathematical model of a neural network, because neurons, we didn't know much about neurons much before the 1930s. And so they created this neural network, this Macaulay-Pitts neuron based on the work of Alan Turing on computable numbers. So what they did was they provided a way to describe how our brains work, like the brain functions, in very abstract terms, rather than listing it in sodium potential and electrochemistry and all of that. They figured out a way to make it to to display it in very abstract terms, and they showed that like the simplest elements connected in a neural network can eventually combine together to provide very like immense computational power, right? And initially in the 1940s, during wartime, and early in the 1950s, this wasn't very popular because machines, ENIAC, and all the very early computer models were not powerful enough to implement this in a way that it outperformed statistical models, right? Because pure statistical models, at the initially at least, are always going to outperform artificial neural networks, because as we'll see later, neural networks are universal approximators, and powerful statistical techniques are very targeted towards solving individual problems. Right. So until like John von Neumann, Norbert Wiener, all these other people, when they started applying these ideas, that's when Macaulay-Pitts became the fundamental Macaulay-Pitts neuron model became popular, right? So initially, I mean, the neural networks right at the start, like when the perceptron model came out, people were thinking that okay, in 10 years, in 5 years, we'll be able to recreate the human brain, and we'll be able to like essentially approximate our way into creating like artificial intelligence very soon. Well, that didn't work because people hit the limitations of hardware more than the limitations of like math, right? So because of this, because it was almost impossible to train like a powerful neural network in those days, in the 60s and 70s, the field essentially died down. Right. There were some applications. For example, the U.S. Army and the U.S. Navy were using some versions of artificial neural networks for cryptography, and also for signals intelligence, and also for facial recognition. But those were always falling back on statistical techniques over neural networks. Lots of new algorithms came out. The perceptron model, like in 57, in 1957, was a very powerful milestone in the development of neural networks. But in the 80s, people came up with a technique called backpropagation, which we'll learn later. And because of this backpropagation, and then layering these perceptron models together in what's called multi-layer perceptrons, Geoffrey Hinton, David Rumelhart, Ronald Williams, these people in the 80s, they essentially broke through the hardware limitations of artificial neural network. And you will find that these people, the people who created these things, like Geoffrey Hinton, for example, they are still like giants of the modern deep learning and the modern artificial neural network AI world, right? Um, so yeah, that's how we crossed together the 60s and 70s AI winter, so-called AI winter. But what's up? The Zor problem, yes, yeah. It is one of the, before we started layering together multi-layer perceptrons and before we started backpropagation, various fundamental binary operations couldn't be done through this.
So a couple questions about that. Was it the back propagation or the layering that wasn't able to overcome the XOR?
The MLP was able to like cross over, and but both of these ideas came together like almost at the same time, right? That's how they managed to kind of solve. Yeah. So, but what were like? Okay, we know what artificial neural networks, how they were being built, but what was the driving goal for having neural networks versus pure statistical methods? Well, the big thing that computer scientists in those days and mathematicians in those days, what they really wanted was something called a universal approximation. So a universal approximator, which powerful neural networks are is a model that can learn any relationship between any given input and any given output given enough training data and assuming that you have been able to layer them correctly, it should be able to approximate any given function to any arbitrary degree of accuracy. So not just very simple functions like logic gates or whatever. So one of the fundamental like solutions to like latch gates, D latches, F latches, all of those were very accurately solved by artificial neural networks, but people still didn't use them because they weren't solved for all cases. So you would be able to initially find edge cases where the neural networks were going to give you bad results, for example. Uh, and statistical methods for universal approximations, like Newton's method and lots of other different methods, also had this problem that they were not truly universal, right? But later on, like George Sarbajna proved it in the 80s, that a feed-forward neural network uh, with multiple hidden layers can essentially, given like using a finite number of neurons, can approximate literally any function that you throw at it, and artificial neural network is going to be able to approximate it, which is still to this date the big draw of neural networks, that you give it any set of data and you tell it this is the kind of output that I want from it, and the neural network is going to be able to do that for you. It doesn't matter what kind of data it is, doesn't matter what kind of output it is. If there is a mapping somewhere in the space of solutions, it is going to be able to find it. It might take time, it might not be efficient, but it is going to find it. So that is the big draw of a neural network, the universal approximation. So the UAT, the universal approximation, like I said, it was proven by Josai Benko and Kurt Hornick. Like I said, a feed-forward neural network with just one hidden layer containing a finite number of neurons can approximate any continuous function to any arbitrary accuracy. Right. So this bit of complex mapping between input and output, that has what has made artificial neural networks and modern deep learning so very powerful for all kinds of solution. While like this is theoretical, right? So theoretically, they can represent a neural network can represent any function. Like you give it any input and any output, and it's going to be able to discover the function between them. But the challenge for us and the challenge for all developers and computer scientists is effective training, uh, avoiding overfitting, generalizing, like all these little things. This is what like is our responsibility as computer scientists to solve, right? Because otherwise they essentially work themselves, they train themselves, and we have nothing to do because they end up being black boxes. Like we don't know what all the neural connections are doing. But understanding what they're doing and improving their efficiency, that is what our our job as computer scientists in this field are. So, um, what do I mean? Universal approximation works on linear and nonlinear data, right? I should have mentioned this. So adjusting the weights of the neurons, we'll talk about what that means later. They can model both linear and nonlinear relationships, which is again what you would assume a universal approximator to be able to do. But what does it mean that uh, linear and linear data sets and nonlinear data sets, right? So what means is that if your data is not linearly separable in one dimension, right? This is a one-dimensional data set, and you cannot find a linear function that separates it, right? The separation has to work something like this, and obviously, this is not a linearly separable uh, a function, right? But this is where neural network comes into handy. Now, this is another data, right, where the data is separable in the x square space, right? So again, you would need a separator like this to separate the data. So when you're training the model, one of your inputs, like uh, if the input data is like this, the class is say 0, and if the input data is here, the class is 1. Similarly here, if this is how your data is coming in, and this is what your neural network has to identify, right? So this is what the output of your statistical model neural network model has to be. So this is what we are trying to do, and this is what the very first neural networks were designed to do. So this is what the very first Machalopate's neural networks look like. Like I'm showing this in a modern term. Like these visuals are more modern. They did not exactly show it this way, but what you see here is a very basic model, right? So you multiply the weights with the inputs, and that's how you get the data. And you see here this is the separation. This boundary is what the neurons are trying to create, right? So when the inputs are 0, the output is also 0. And for an OR gate, sorry, here, if any of the inputs are 0, then the output is a 0. And if all the inputs are 1, all the inputs are high, the output is high. So that's an AND gate, and that's an OR gate. And this is how this line is what a neuron, a very simple neuron that you see here is trying to create, right? This has no hidden layers. This is just like one neuron, right? That's all there is to it. Just weights and an input. But yeah, like you pointed out, XOR cannot be done in this. You cannot model a XOR gate, an exclusive OR gate in this way, right? In a single layer network. But you can do it using a two-layered, two-unit network. So this is how you would solve uh, an exclusive OR, right? So you have, for example, this H3 is coming after you multiply W23 and W13. That's how you get H3. And so I'll show you the computations later. So this multi-layer perceptron network, which came up in the 80s, this is how you solve exclusive OR. And as you move further on with two more and more complicated functions that you're trying to approximate, the length of your neural networks extend. But in the end, almost anything can be approximated by just one hidden layer. This one hidden layer and a finite number of neurons, you can approximate any network. What's up? So this is this is a function that you're trying to approximate where the output is high if two of the three inputs are also high, right? And the output is low if less than two inputs are low. And when you're building a neural network, well, all you see is like as an end user, as an output, all you see is just this, right? But as developers, we need to figure out how to assign the weights. What are the initial starting weights? What is the what are the values of the hidden layers, etc., etc. So this is what it does, right? So this is the output node function. So the values of the input nodes are multiplied together, multiplied and added together uh, to get this output, and this particular function is going to give you this output, right? So again, we'll work out a couple of problems like this just to see how these results are calculated. But I wanted to show you a very basic ANN just to show you how, like, for arbitrary functions, what it looks like. So, um, well, there are various types of topologies. Like you saw, this is one topology. This is another very simple topology for neural networks. In general, like single layer perceptrons are obviously not very well used these days because they're not powerful enough for our problems, solving our problems. Uh, any neural network that you see, whether it's very complicated ones like LLMs or ones that you can work out by hand, are all multi-layer networks, right? Multi-layer perceptrons. And obviously, there are also different types called feed-forward networks where the weights move forward, and recurrent networks where a different type of backpropagation is done, things like that. And there are activation functions. So when you come to the output, when you come here to the output node, how does the value that you have created, how does that correspond to an output, right? Like how high should it be or how low should it be for a neuron to fire. So for individual neurons, if you have multiple neurons, like how high or how low should a weight be, should the value coming in be for that neuron to fire and propagate its value to the next chain. So that is calculated by various types of activation functions. So linear, sigmoid, tan, sine function, etc., etc. Sigmoid is very popular because sigmoid doesn't fall into the negatives. But for different purposes, you'll use different types of activation functions. There are websites that I'll link later where you can take a standard data set and then you can test out different types of activation functions to see what the output results are, right? So for a multi-layer neural network, what are hidden layers? I've been mentioning hidden layers before. So the intermediary layers between what your input is connected to and what your output is, those are hidden layers because you don't see how they are layered, what their weights are, what their connections are when you're looking just at the output and you're looking just at the input. And they are controlled by these activation functions. Right? So, so this is a structure of an arbitrary artificial neural network where you have many input layers, where you can have multiple hidden layers and one output layer. What does it mean when you train it? Well, when we're training a neural network, what it means is that it learns the weights of these connecting lines, right? It learns uh, through trial and error, and by running it multiple times, you figure out what set of weights for each layer brings you closest to your desired output. And you do this by running it once, seeing how far the output of the neural network is from your required output, and then based on that you modify the weights and then you run it again. So it works in a loop, and it after a while, after a finite period of time, which is important because you don't want a model to run infinitely to get close to your results. After a finite period of time, it is going to come close enough to your output data. That's the entire purpose of a universal approximator. Given time, given finite time, it comes very close to your to what your required output is. So, uh, this is mostly for your review. So all the terms that I've been saying beforehand. So this is a review of what all of them means. What are units? What are links? What are weights? What are activation functions? What do I mean by architecture? What do I mean by single and multi-layer? So use this slide when you're reviewing for your exams or whatever, or when you have trouble when I'm talking about some particular term and you don't know what that term is, this will come in handy. They are just a list of terms, right? I think I've mentioned all of this. Loss functions are, like I said, if your output is far, if this y that you're getting is far from the y prime that you're getting is far from your desired y, that difference is handled by loss functions. And then the goal of a universal approximator, the goal of a neural network, is to minimize this loss function so that you can come as close as you want to your input, right? So this is a mathematical description of a neural network, which is a function that goes from x to y, where the domain of x is natural numbers and or rational numbers, and the output is either high or low for every one of them. So it approximates real valued, discrete valued, and vector valued target functions. So I've shown this before. The sine function that you see here for the hidden layers, this is how the sine, let me show you. I think there's an explanation of the sine function somewhere. Yeah, so this is what the sine function is. So if x is greater than or equal to 0, it's high or positive, and if it is less than 0, it's negative. That's the very basic. So it's kind of like it's a very simple function, but it's very useful in things like this. So this is how you would calculate the output O5. These are the hidden layers H3 and H4. So how you would calculate this is multiply the inputs with the weights and subtract it from a training value, and that's how you're going to get the outputs. So the trainable parameters are these weights and these strings, right? So neural networks are, like I said, they're universal approximators. So they are general purpose supervised learning methods, right? So they're extremely powerful. You all know this. Um, but so given that they are a general purpose supervised learning method, how do we learn? Like, how are these weights calculated? Well, the best and the earliest, one of the earliest methods for learning, called the backpropagation algorithm, is also really, really powerful. And it works like you would guess from the name. It propagates the errors backwards so that you update the weights every time it learns. And that's how you update the weights, and that's how you get closer to the actual value. So let's zoom in to like an individual node, an individual unit in a neural network. So what does it get like as an input? So just a single node. So this bit, this threshold unit, that here you see these threshold values, right? So that they are the ones who introduce the nonlinearity, which is why we moved from just being able to solve like very simple and or to more complicated exclusive or, is to introduce this kind of a nonlinearity, right? You take the inputs, you multiply them with the weights, and then you subtract some threshold value with which works here as a activation function, and that's how you get the output. Now, remember very clearly, this kind of multi-layer neural network, what it provides is it's not differentiable, which means you can't learn via gradient descent. What's gradient descent? I'll either talk about it today or Dr. Eick will talk about it later, but I'm just pointing it out right now so that you know that this kind of multi-layer neural networks are unsuitable for learning via gradient descent. Now, the neurons are modeled by this unit connected by these linked weights, and which is then sent to, say, for example, this is a sigmoid function. It's sent to an activation functions, and that's how you get the output, right? And this is how you define the net input and net outputs. Of the summation of all the weights multiplied by the current value of the node itself, and the output is calculated by applying the activation function, which in this case is sigmoid. You apply the activation functions to the threshold value, and that's how you get the output, right? So any Boolean function, like I've said before, can be approximated by a two-layer multi-layer perceptron. Any bounded continuous function can be approximated by a two-layer network. Sigmoid functions are very popular. They provide a set of basis functions from which any arbitrary function can be composed. So that's how you'll see that. That's why you'll see that a lot of very fundamental mathematical functions, they all use the sigmoid activation function rather than the sign. In some, you'll see in what cases we use tan or in what cases we use logistics. But if you don't know what activation function to use, just default to sigmoids, right? And if our function is neither bounded nor continuous, that is, it's a discrete unbounded function, as soon as you move to three-layer networks, even that can be approximated, right? So again, we're moving closer and closer to like the perfect universal approximator. So now that we know what neural networks are as much as we can, so how do you think we make predictions? Question, just like given we have a neural network and you have seen what it does, how the outputs are created. So how do we make predictions from a neural network? And he guesses it's very simple. It's not a very complicated answer. What's up?
I guess, what do you mean by predictions?
So you have trained your model on your data. Now you want to figure out like what is the model useful for, right? You need to figure out whether given new data, it's able to come up with new answers. So how does the neural network do that?
It takes input values and then multiplies them by the weights of the hidden
Yeah.
layers. It conveniently does that depending on the number of hidden layers.
Yeah.
And leaves that output.
Yeah, it's you just to make predictions on new data, you just run the neural network. And this time you're not doing backpropagation, this time you're not doing training, you're just running it forward. And then when you get to the end, that's your prediction, right? That's a very fundamental of a neural network of any kind of model. Once you're finished training, the model is fixed, and that's it, right? So, like I said, given the input, you go through the entire neural network without. This time you don't update the weights. This time you don't train it, and you get to the output. So given a neural network, what is the one bit of information you need to know to define it, right? What is the most important information in a neural network that you need to define it? If you meant the weights, yes. The weights, that's all you need. You also need the number of layers, but if you have been given the number of weights, you can intuit the number of layers from that. So the entire definition of a neural network, which is why they are stored in tensors or matrices in modern deep learning, you'll find that you define like your stored models are stored as weights. Like they're stored as like multidimensional tensors, which are stored as just the weights. That's all you need. So, but neural network predictions and deep learning predictions, they're super fast and they're super efficient. So why do you think that is? Like, why are they? What fundamental feature of a network like this makes it so fast? Guess. Yeah. Yes, but for a big network, there's the math may be simple, but there's still a lot of math. I'll answer it for you. Well, the fundamental feature is that these are all working parallelly, right? So it's extremely incredibly parallelizable. It's so for example, if you have learned in your architecture classes, single instruction, multiple data, single instruction, individual single data, SISD, SIMD, all of that, uh, neural networks are extremely parallelizable, which is why they run super fast. Because your CPU or your GPU in most cases is not bottlenecked waiting for data to come in. It is continuously performing its own calculations and it's moving very, very fast. So finally, what does it mean by expressive? What I mean is that why are neural networks universal approximators? what little bit of it makes it expressive, what little bit makes it then a universal approximator.
The amount of weights that's so dedicated.
Yeah, well, kind of. What I more mean by that is the units, right? The way the nonlinear units, the way the weights are being connected to those nonlinear units. Yeah.
The more ways where you need to.
Yeah. Well, obviously, it doesn't. The number of layers is important, but what is more important is the units themselves, the nonlinear units themselves. Right. So I've shown this image to you like a million times right now. So let's calculate like a real example of this, right? So I'm showing you this because almost inevitably this is going to be in one of your exams. Not this, it'll probably be involving backpropagation, but this is how neural networks weights are calculated. Say for example, in this training example, the input one is one, input two is also one, A3 is A5 is one. So like the required output is also one. All the initial starting weights are 0.1 except for W4 weight 45, which is 1. Gamma is the learning rate, which is 0.2. And the activation function that you're using is a sigmoid activation function, right? So you will almost certainly be calculating for one of your exams, you'll be doing this, right? So how do you calculate this? How do you calculate A4? Well, you apply this gamma function, this sigmoid activation function to you first for A4, for example. So you take W14, multiply it with I1, and then here it's X1, it should be I1, whatever, it doesn't matter. And then you take X2 and you multiply it with W24, you get 0.2, and then you apply the sigmoid activation function, you get 0.55. You do the same with A3, then you calculate it for A5, which is where you take in these two and you get this. So your value is 0.647, which is not 1. So your error is 1 minus 0.657. So you have a 35% error, right? So this is without backpropagation. So this is just one run of it. Late in your actual exam, you'll probably be asked to do this with backpropagation, which I'll show later. So gradient descent. Well, gradient descent, remember there are some two-layer, multi-layer perceptron doesn't really work with gradient descent, but what is gradient descent? So we need to figure out, like here you have just one error value, right? In broader cases, you'll have a set of errors for every single nonlinear unit. So what gradient descent does is that we are trying to minimize this loss function. We're trying to minimize this error, trying to get it as close to 0 as possible. So that's what gradient descent does. So given a set of examples and given an error function, you modify this vector of all these weights, W1, W2, W14, W24, W35, W45. You modify them so that you are coming closer and closer to the lowest possible error, right? So this is what gradient descent is. Now, it is very easy to miss this minima. And so, for example, if you're modifying all the weights by a certain step, say a step delta, and your delta is too large, it is entirely possible to jump from this location where you are close to the minima but not quite, and then jump to here. And then as you continue, you'll find that the error is again starting to go up. So gradient descent is finding this minima, right? And there are various ways and various traps. Like you can get trapped in local minima. So for example, if this is a valley and this might continue down and there might be another much lower optimal value, right? So again, so there are multiple different ways of handling this. I'm not going into it right now, but that's kind of what it does. So this weight vector, it tries to minimize this. So you can see as it's moving, it is why is it called gradient descent? It is moving along the direction where the slope is the highest, right? It is producing wherever the steepest descent along this surface of this error is. Now it is very dependent on where you start. So if you start, like I said, it is entirely possible to start on a saddle point, which I have personally faced, where I was training a model to find roads, like most optimal paths between locations within a city. And what I was doing is like several of my starting locations were falling on saddle points. So you see this is a valley, and but there might be, instead of a further valley, there might be smaller saddle points in between here. So if your gradient descent function starts on one of those saddle points, it is very easy to get trapped there, where you move along the direction of steepest descent, and then it starts increasing again, and you think that okay, you found the best position, and then you try to locate it, and then you ping pong between that saddle point, and you never get even close to the actual minima. The way to avoid that is there are many various ways, but one of the easiest ways is to add something called temperature, where your initial starting points are arbitrarily scattered at certain intervals. Yeah. Okay. So this is how gradient descent works for a multi-layer neural network, where your weights are updated according to this formula. Your initial weight subtracted from this lambda times this differentiable value, this error differential. The error function that you see here is the standard error function for gradient descent. Um, you can memorize it if you want, but in general, like I said, your exams, everything are going to be open notes and open books, so you don't need to. It's useful for you to know, because when you're working on it, you don't have to consult your stuff every single time. But this is a very standard error function that in practice is never used, because you'll see that real life error functions get way more complicated. They introduce a lot more terms to this, but this is the very basic error function. But one of the things you note here is that whatever activation function you're using here must be differentiable, right? So if your activation function is non-differentiable, it does not work. So for example, I think uh, the sine function doesn't work here, I think. But there are some activation functions which are not differentiable and are used in very highly targeted specific cases. So don't use them here. Okay, you have time. So for sigmoid function, this is what it's going to look like, right? So this is the weight uh, lambda times this particular value. So applying the sigmoid function to this part, this is how you do gradient descent when your activation function is a sigmoid. So neural network learning is mostly this gradient descent, steepest descent hill climbing for a differentiable error function. Now, there are some things that you need to know. So how far you jump, so that delta value is dependent upon your learning rate, on the error, and on the input activation value of the node itself, right? So depending on your current weight vector, like whatever the vector of like W13, W23, W14, W24, all of those weights, you apply the gradient of like you apply the steepest gradient descent, you get a new weight vector, and how far this weight vector has moved depends on these three factors, right? Now the biggest factor that you can control is alpha. Alpha is your learning rate, and the learning rate. If your learning rate is too slow, it'll always come to the very close to universal approximation, but it's going to be very slow. And if it's too high, you're going to jump over the this minima, right? So you need to figure out a balance between them. You'll find that like training alphas can be like something like 0.001 or 0.01. So for some of your problem sets, we will ask you to try like very high alpha values like 0.1 or 0.9, and then we'll ask you to try very low values, and then you'll see what the outputs are, kind of. So this should be playing. Hang on. Oh man, this was supposed to be a GIF. Whatever, doesn't work. I never trust GIFs or GIFs. So this is what error functions look like. So they start at some point and they're trying to figure out this minima, right? So this is what like a practical error function looks like. So this is the gradient field. The function that is being approximated here is square root of x squared plus y squared, and this is the gradient field on that. So based on where you start, this is the location of your movement. So we walk in the wherever your weight vectors are starting from, you walk in the inverse direction, kind of trying to come to the center point, right? That's how the steepest descent gradient works in practice, right? So how do you learn? So now that we know how steepest descent works, how is it used in practice, right? So learning with a multi-layer perceptron is very simple, like similar to what you have done before. So the problem here is that you have a set of weights, right? But the weights that you are seeing from your output is only the latest, like from the weights on the final layer. So we don't get feedback in the intermediate layers that are before the final layers. So the how we have set this up is that if your activation function, for example, sigmoid is differentiable, then the output of the network is also a differentiable function of the input and the weights, right? So we define an error function, in general SSE or MSC, sum of squares of error or mean of squares of error, that is also a differentiable function of the output. And then we evaluate the derivatives of the error with respect to the weights. And we use these derivatives to find the weight values to minimize error function, right? Because the slope, as you know, del x, del v is essentially the derivative. So that's how you find the direction of steepest gradient. That's how, like, this is the most basic optimization method, and this is what we'll be using in class. But if you do this, like if you find the final weight and then you apply different, like you evaluate the derivatives backwards, well, now you have come to backpropagation. So this entire process is backpropagation. This is what Jeffrey Hinton came up with in the 1980s, and this is what we still use. Okay, so now that we know this, small question. So what is the chain rule? I hope all of you know this. So if you're differentiating a function that is a function of something else, how do you do this? Right.
You take the prime of the, you take the f prime of the bigger function.
Yeah.
And multiply it by the, with the smaller function.
Yeah,
inside,
yeah,
And then you multiply that by.
yeah.
G prime.
Yeah, that's essentially the chain rule. Yeah, that's pretty much it. So in practice, this is what you end up doing. Where is my mouse? Okay, and there. So this is what you are going to be end up doing for backpropagation purposes. So let's go step by step in backpropagation. So gradient descent, you know that what it means is that you change the weights in the direction of the gradient so that you are able to minimize error functions, right? So this is what backpropagation does. This is what chain rule is to calculate the weights of the intermediate nodes, like the weights of hidden layers 3, then 2, then 1. You use the chain rule for this, and this is what you end up. And you memorize the weights to make the updates faster. This you don't have to know, but you don't have to do this on your own. This is done by the networks themselves, but this is how you do it very quickly, because in bigger networks you have millions and millions of connections, right? So if you're remembering and if you're doing all of these, any weight that doesn't change, you don't have to perform the differentiation on those, right? So you loop over them. The forward step is what you know. So given the input, you make the predictions layer by layer, starting from the first layer, like I showed you in the example. And then in the backward, like this is what you see it. In the backward step, then you calculate the error, you come to the final y prime, you subtract y prime from y, which is the output, and then you update the weight, then you update the weights again, but this time starting from the final there, right? So this is what the backpropagation algorithm is. So if you want to implement it by hand, this is what you're going to do. But let's just do it by hand. So what does it look like? So this is slightly different, and this is probably what you're going to actually get in your actual exam. The way values are going to be different, but you're going to get something like this. So you have your what are you doing? So you know the forward process. The forward process is very simple. So this is the backward process, right? So how are you updating the weights? So you have the old weight, right? Then what you add to it is the current value. You multiply it with the activation function, and then you multiply it with the associated error, the delta error that you have gotten from the final value, right? So from A5, whatever your initial output was, you subtract that from your desired output, and that's how you get delta 5, right? This is the error, and that's how you start calculating. Wait, it was supposed to come in this, whatever. The animation didn't work. So this is how you start calculating it. So this is how the forward process works, right? This is what I showed you: A4, A3, and A5. Then you calculate the error. Now that once you have the error, you calculate the error for the previous values as well. And then once you have this delta 5 error, then you start updating the weights, right? Your gamma is your learning rate. You multiply it with the current value of A3, which was the previous value of A3, and then you multiply it with the error. And this is how, and you do this layer by layer by layer, and you get the value. Now, what are the new values of A4, A3, etc.? That is, you get the value you get once you have these weights calculated. Because remember, you're updating the weights, not the value of the nonlinear units. So what are the values of the nonlinear units? Obviously, you take the new weights and then you apply the activation function like you have done normally. So so step by step, what you do is you run it forward once, you get the value, then you get the error, then you back propagate the error over all of these then you end up changing the weights. Once you have this new set of weights, uh, you apply those weights, and then you get the new values for A3, A4, and A5. So you see your A5 value has changed slightly, right? So yeah, your new A5 from initial, it has changed to 0.6483. So it's coming closer and closer to 1, the actual value, right? So if you have any questions, like if you're having trouble understanding this, work through it by hand. DM me or DM any of your TAs on Teams, and I will help you during our office hours or any other time. I'll help you work this step out step by step. If you're having trouble just doing it, take a pen and paper and go through this once. That'll help you understand how it works better than I can tell you right now. Okay, so some of the problems with training is that you can't really guarantee convergence. Like it will almost certainly converge, but there's no guarantee of convergence, right? Like I said, in one of my own research, the model itself was far more complicated than this, but it never converged because I kept falling on saddle points because of a small problem of how I was initializing my values. I kept dropping on the exact saddle points, and I was never converging. Even if while I was running it on the HPC, like my model was running for 6 days, 7 days, continuously, and it was still never coming even close to convergence. Well, the solution to that, like the way I later solved it, was like a combination of various different temperature parameters. But like I said, neural networks can form non-convex functions with multiple local minima. So whatever value you are stuck in might not be the true global minima. In practice, like in the real world, one other way of solving this is getting lots of data. Like if you have huge amounts of data to train it on, the chances of you getting stuck on any local minima goes down. It's not, this is only possible because memory these days is much, much cheaper than processing time. So you can train your models on huge amounts of data, on very large data. That's how these modern large language models or Mid-Journey or any of these uh, generative models work, is because the data is very cheap. For adequate training, like I said, it might take a long time and it might take many, many hours of CPU time. Some of you have worked with HPCs in the UHHPC, so you know you can request CPU time, GPU time, how many CPUs, how many GPUs to run your models. And then you have to figure out how to terminate. So you can essentially run your models infinitely. I've done that before, but to stop at a reasonable time, you need to set up termination criteria. Termination criteria can be anything, but the most common threshold is that your error isn't decreasing, right? Now, there are other termination criteria. If your error is increasing at a certain rate, or if if the rate of change of your error decrease has gone to like some certain value. So there are many ways of dealing with this, but the very basic way is that you check whether your error is decreasing or not, and if it's not decreasing, then you stop training, right? And to avoid this local minima problem, you run your model several times with several different initial weights. Uh, for different techniques. So, what's up?
Is there any strategy?
It's essentially random, right? You have a large solution space, and you want your initial data to cover as much of it as you can, depending on your training method. Now, there are certain other training methods where you divide your solution set into like quadrants, and then you try to explore each of those quadrants very thoroughly. So there are multiple ways, but what it comes down to is that you spread out your initial values enough that you don't get stuck in a saddle, right? One of the biggest dangers of neural networks that you will find in your training as well is overtraining, right? You overfit your neural network to your input data set, and as soon as you get something that is out of band, your model does not know what to do, right? So this is you will see this, like this is very obvious in large language models or generative AI or stuff like that. If your model has been trained, say for example, some of you may have heard of it. There was a Microsoft chatbot like 5 or 6 years ago, I think, that was trained on the internet. And a large amount of the text that it was trained on came from websites like 4chan or whatever, where there were no filters. So end users very easily managed to turn this chatbot, which I think was called Tay. It managed to turn this chatbot into like extreme racist. Right, because it fit on that data, right? It fit on that 4chan data, and then if you talk to it, if the input that you're giving it is very similar to the input that it was trained on 4chan, it's going to give you output that 4chan people were giving it. So the chatbot became very racist, unfortunately. So there are ways of dealing with this. Like the easiest way of dealing with it, and what most people do, is that you sanitize your outputs. So whatever your outputs are coming from your large language models or your generative AI, you run it through another different model to check whether the outputs are good or whether it's leaking data or something like that. Another example of overfitting is that I don't know if any of you have used GitHub Copilot, which is a training tool, which is a coding assistant tool. So if you're coding and if you have GitHub Copilot active on VS Code or Eclipse or whatever IDE you're using, it's going to give you suggestions, right? So what people figured out early on with GitHub Copilot is that if you type API key equals, it's going to randomly pick an API key that it has trained on. Or if you say password equal to something, and then it's going to pick a random password that someone may have accidentally left in their GitHub distro that nobody has ever seen, but the model has trained on. So it's going to rip that password out and give it to you, or rip out an API key and give it to you. So again, these are problems with overtraining and overfitting. So like I said, there are various methods of solving it: validation set, testing accuracy, early stopping, cross n-fold cross validation. There are multiple different ways, right? So to prevent this like overfitting, like one of the other problems, like this doesn't really happen. The first problem that I've pointed out here, like hidden units, but like because memory is so cheap and processing power has also kept up fairly well, the too few hidden units problem doesn't really happen. But if you are training your model for to run on the edge, for example, if you're training a model to run on smaller chipsets or on cell phones, you might be tempted to shrink the number of hidden units, and so that your model has once your model has worked very well, you know what your model is stable. You reduce the number of hidden units and you send it to an edge device. Well, that also creates a problem because it learns the initial data too well and it fails with out of band data, right? And obviously there's a balance. There's a good midpoint between too few hidden units and too many hidden units. There are cross validation methods that you can use to approximate how many hidden units are necessary. Um, and another really interesting method of dealing with this is called weight decay. Weight decay is done so that every time you're training your model, your weights like decay slightly, right? And what it does is that your because your weights don't like become too heavy or too, it doesn't overtrain and overfit on certain input data, right? Um, I think we're pretty much done, but okay, yeah. Since we have dropout, let me tell you what dropout is. So Jeffrey Hinton, who came up with backpropagation in the 80s, came up with something called dropout. So what it does, dropout is very interesting because sometimes it leads to really, really good results. So what it does is you have trained a model and you have lots of hidden layers, you have lots of nonlinear units within those hidden layers. What dropout does is that it randomly deletes some of them, right? With given some probability p, there is always a chance that, say for example, there's a 1 in a million chance or 1 in 10,000 chance that one of these hidden layers is just going to be deleted at random. Now, this doesn't have to be at random. You can say that if one of the weights of the hidden layers is not changing, or if the value is too low, if the weight for a particular hidden layer falls under say 0.05, you drop it, you delete that hidden layer. So and this continues over and over again until you have something like very optimal, right? And eventually you can, like what Jeffrey Hinton figured out, is that for some neural networks you can drop up to 50% of the hidden units and 20% of the input units, and still your output is going to be really good, right? So this is how dropout training kind of works. So what this does is that it figures out what are the most essential neurons within the neural network, and everything else can get dropped. So this Jeffrey Hinton came up with this because this is similar to how the human brain works, like neuroplasticity. That's how neuroplasticity works. So anything that like the brain constantly repurposes neurons so that any that's how you lose memory, right? If you're not using something, if you're not trying to constantly recall something, you end up not remembering it as well. So this is kind of what dropout does. So that's this is pretty much it for today. Here are a couple of websites that you can play around with, like the TensorFlow Playground, and then neural network from scratch.io and nfs.io. But this TensorFlow Playground is, which one is skip verification? Okay. So here you can see that you can pick what your input function is. You can pick how many neurons there are, how many hidden layers there are. You can pick your activation function, regularization, rate, etc., etc., and then you can run this, and you can see what it looks like with some inputs. You can see that the model has very quickly converged and giving you good results, right? So if you want to see what these neural networks look like in practice, this is a really good website. Okay, that's it for today. And well, if you have any questions, contact me on Teams.
Hey, can I draw something?